In 1977, we launched a spacecraft called Voyager 1 into the darkness beyond our world, and we never stopped listening. Nearly 50 years later, that spacecraft is no longer inside the solar system. It is moving through interstellar space, farther than anything we have ever built, and somehow the conversation is still going. It passed the moon within hours. It crossed the orbit of Mars within months. It moved through the asteroid belt, past Jupiter, past Saturn, and then into a region where the Sun becomes just another distant star. And still, after all this time, we are able to hear it. The signal that Voyager 1 sends is unimaginably faint. By the time it reaches Earth, it carries less energy than the random noise inside the electronics of our own instruments. It spreads out across billions of kilometers of empty space, weakening with every passing second. And yet, it arrives. Welcome to Sleepy Time Universe, where the largest questions in science unfold slowly in the quiet rhythm of a calm night. Tonight, we explore how that connection is possible, how a signal, weaker than anything you could feel, continues to cross interstellar space and reach us here on Earth. We will move through the journey of Voyager 1, from its launch in 1977 to its passage beyond the edge of the solar system. We will look at the physics of communication across vast distances, the engineering that makes it possible, and the quiet network on Earth that is still listening. If you enjoy this kind of slow exploration, you are welcome to subscribe. Now, let's begin. Chapter 1. Born in a window of opportunity. In the mid-1970s, a group of scientists and engineers at NASA's Jet Propulsion Laboratory began preparing for something that would not be possible again for another 176 years. The outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, were drifting into an alignment that would allow a single spacecraft to visit all of them in sequence, using the gravity of each planet to accelerate itself toward the next. This alignment required precise timing. The launch window opened in 1977 and would close within a matter of weeks. Missing it would mean waiting until the 2150s. The opportunity had been identified more than a decade earlier by a young aerospace engineer named Gary Flandreau, who in 1965 was working at JPL as a summer student. Flandreau was tasked with evaluating possible trajectories for future outer planet missions, and what he found changed the scope of what NASA would attempt. He calculated that a spacecraft launched in the late 1970s could use Jupiter's gravitational field to accelerate toward Saturn, and from Saturn continue outward toward Uranus and Neptune, all without additional propulsion. Each planet would act as a kind of cosmic relay, bending the spacecraft's path and adding velocity through a process known as a gravitational assist. The trajectory was extraordinarily precise. A small error at Jupiter would compound into a significant miss at Saturn. But if the geometry held, a single spacecraft could complete in 12 years what would otherwise require 30 with direct propulsion alone. NASA began serious planning in the late 1960s, though the full Grand Tour concept was eventually scaled back due to budget constraints. What emerged was a more focused mission targeting Jupiter and Saturn, with the possibility of extending to Uranus and Neptune depending on spacecraft health. 2 probes would be built, each one nearly identical to the other, providing redundancy and doubling the scientific return from a single launch window. Voyager 2 departed first, lifting off from Cape Canaveral on August 20th, 1977, aboard a Titan III rocket. Voyager 1 followed 16 days later, on September 5th, 1977, placed on a faster and more direct trajectory that would allow it to reach Jupiter ahead of its twin. The naming reflected arrival order rather than departure order, a small detail that has caused mild confusion ever since. Voyager 1, despite launching second, was always intended to arrive first. Both spacecraft were built around a central electronic structure mounted on a 10-sided aluminum frame, roughly the size and mass of a small car. From that central body extended a series of booms and platforms designed to keep sensitive scientific instruments away from the spacecraft's own interference. A 3-axis stabilization system allowed the probes to hold precise orientations in space without spinning, which was essential for both pointing instruments at targets and keeping the main antenna directed toward Earth. The instruments themselves covered a remarkable range of scientific disciplines. Each spacecraft carried imaging systems capable of resolving features on planetary surfaces and moons. Magnetometers measured the strength and direction of magnetic fields along the flight path. Plasma science instruments sampled the charged particles streaming outward from the Sun. Cosmic ray detectors tracked high-energy particles arriving from beyond the solar system. Infrared and ultraviolet spectrometers analyzed the composition and temperature of planetary atmospheres. Together, the instrument packages were designed to return as complete a portrait of the outer solar system as the technology of the 1970s could produce. At the heart of each spacecraft's ability to communicate with Earth was a parabolic dish antenna, 3.7 meters in diameter, mounted at the top of the central frame and pointed permanently back toward the Sun. This antenna, known as the high-gain antenna, was the primary channel through which all scientific data and engineering telemetry would travel. It was not steerable in the traditional sense. Keeping it aimed at Earth required rotating the entire spacecraft, a maneuver that mission controllers would coordinate carefully throughout the decades ahead. The launch itself was unremarkable in the way that well-prepared things often are. The rocket performed as expected. The spacecraft separated cleanly. Instruments were powered on in sequence. Within hours of leaving Earth, Voyager 1 was already farther from home than most people would travel in a lifetime, and it was only just beginning. What the engineers at JPL had built was not simply a scientific instrument. They had built something that would outlast the careers of everyone involved in its creation, outlast the institutions that funded it, and outlast the era of technology in which it was conceived. They had built, without quite intending to, a message in a bottle addressed to the rest of time. Chapter 2. What Voyager 1 carries. By the time Voyager 1 cleared the immediate vicinity of Earth, it was already a fully operational scientific laboratory. Everything it would ever need to complete its mission had to be on board from the moment of launch. There would be no resupply, no repair crews, no opportunity to swap out a failing instrument for a newer model. What was bolted to that 10-sided frame in 1977 was all there would ever be, and the people who built it knew that. Every component had been selected, tested, and reconsidered with that constraint in mind. The spacecraft's body was not large by any measure a casual observer would find impressive. The main bus, as engineers called the central structure, measured roughly 47 centimeters in height and was about 180 centimeters across at its widest point. From that compact core extended booms of varying lengths, some carrying instruments that needed to be isolated from the spacecraft's own magnetic and electrical fields, others supporting the antenna systems that kept the probe in contact with Earth. When fully extended, Voyager 1 spanned roughly 5.6 meters from one end of its instrument boom to the other. It weighed approximately 825 kilograms at launch, a significant portion of which was the propellant used for attitude control and trajectory corrections. Power was one of the most critical design challenges. Solar panels were not a viable option beyond the asteroid belt. At the distance of Jupiter, sunlight is already roughly 25 times weaker than it is at Earth. By the time a spacecraft reaches Saturn, it is 50 times weaker still. Beyond Saturn, solar power becomes essentially impractical for a probe of Voyager's size and energy requirements. The solution was nuclear. Each Voyager spacecraft carried 3 radioisotope thermoelectric generators, known as RTGs, mounted on a boom extending away from the main body to reduce radiation interference with the scientific instruments. These devices contained pellets of plutonium-238, a radioactive isotope that generates heat as it decays. That heat was converted directly into electricity through an array of thermoelectric elements, with no moving parts, no turbines, no pumps. At launch, the RTGs produced approximately 470 watts of electrical power combined. It was not a great deal of electricity by terrestrial standards, roughly comparable to a few household light bulbs, but it was enough, carefully managed, to run the spacecraft systems and return data across the solar system. The onboard computers were, by modern standards, extraordinarily limited. Voyager 1 carried 3 computer systems, each with a specific role. The flight data system managed the collection and formatting of scientific data. The computer command subsystem received and executed instructions sent from Earth. The attitude and articulation control system managed the spacecraft's orientation in space. Together, these systems operated with roughly 69 kilobytes of memory. A single low-resolution photograph taken by a modern smartphone contains more data than Voyager's computers could store. And yet, those computers have been running without interruption for nearly 50 years. The scientific instruments represented the core purpose of the mission. Voyager 1 carried 2 television cameras, known as the Imaging Science Subsystem, which used Vidicon tubes rather than the digital sensors common today. These cameras captured images of extraordinary clarity during the planetary encounters, returning photographs of Jupiter's cloud bands and the volcanic surface of Io that remain among the most striking images ever taken of the outer solar system. Additional instruments measured the properties of magnetic fields, plasma, charged particles, radio waves, and infrared and ultraviolet radiation. Each instrument was designed to function over an enormous range of conditions, from the relatively dense plasma environment near Jupiter to the thin, cold quiet of interstellar space. One component of Voyager, one stands apart from all the scientific instruments, not because of what it measures, but because of what it says. Mounted to the spacecraft is a 12-inch gold-plated copper disc, known as the Golden Record. It was included on both Voyager probes at the suggestion of Carl Sagan, who chaired the committee responsible for its contents. The record carries 115 images encoded in analog form, greetings in 55 languages, a selection of natural sounds from Earth including wind, rain, surf, and birdsong, and 90 minutes of music drawn from cultures across the world and across human history. It carries the brainwave recording of Ann Druyan, who was thinking about the history of civilization and, by her own account, about falling in love with Carl Sagan when the recording was made. It carries mathematical diagrams intended to help any finder locate the record's origin. The cover is engraved with instructions for playback, written in the symbolic language of physics rather than any human tongue. The Golden Record was not designed with any specific recipient in mind. The probability that Voyager 1 will ever come close enough to another star system for the record to be found is vanishingly small on any human timescale. The nearest star to our own lies more than 4 light-years away, and Voyager 1, traveling at roughly 17 kilometers per second, would take approximately 73,000 years to reach it, even if it were heading in that direction, which it is not. The record was not a practical communication device. It was something else. It was a decision made by a group of people in the 1970s to include something of themselves in what they were sending out, to acknowledge that they were alive, that they had made things, that they had wondered about the universe and been moved by it. Whether anyone ever finds the record is almost beside the point. The point was the reaching out. Everything on Voyager 1, the cameras and the magnetometers, the RTGs and the antenna, the computers with their 69 kilobytes, and the golden disk with its encoded music, was designed or chosen by human beings working within the constraints of their time and their budget and their imagination. What they assembled was not perfect. Some instruments failed earlier than hoped. Some data was lost. Some questions the spacecraft could have answered went unanswered because of limitations no one had anticipated. But the core of the machine held, and it is still holding now, in the darkness between the stars, carrying its cargo of human curiosity outward into a silence we have only just begun to understand. Chapter 3: The Edge of the Solar System. For most of human history, the boundary of the solar system was a concept without a precise location. We knew the planets. We knew, in a general sense, that the sun's influence extended outward beyond the last of them. But where exactly that influence ended, where the sun's domain gave way to something else entirely, was a question that could not be answered from Earth. It required something to go there and tell us. The sun does not simply end. It does not have a surface in the way a planet does, a clear line where one thing stops and another begins. What it has instead is an influence, a continuous outflow of charged particles known as the solar wind that streams outward in all directions at speeds of several hundred kilometers per second. This wind carries with it the sun's magnetic field, stretching and distorting it across the vast distances of the outer solar system. Together, the solar wind and the magnetic field it carries create a bubble of influence around the sun called the heliosphere. Everything inside that bubble exists within the sun's extended atmosphere. Everything outside it exists in true interstellar space. The boundary of the heliosphere is not a sharp line. It is a region, a zone of transition, where the solar wind begins to slow and eventually stops. The outer edge of this transition zone is called the heliopause, and it represents the most meaningful boundary in our immediate cosmic neighborhood. Inside the heliopause, the solar wind dominates. Outside it, the interstellar medium takes over, a thin and ancient gas of particles left over from the deaths of stars long before our own sun was born. Before reaching the heliopause, a spacecraft traveling outward from the sun passes through an intermediate boundary called the termination shock. This is the region where the solar wind, having traveled billions of kilometers from the sun, begins to slow dramatically as it encounters the pressure of the interstellar medium pushing inward. The solar wind does not stop abruptly at the termination shock. It slows, heats, and becomes turbulent, entering a region of compressed and tangled plasma called the heliosheath. The heliosheath is a thick, churning layer that lies between the termination shock and the heliopause, and it is considerably more complex than the relatively smooth solar wind that precedes it. Voyager 1 crossed the termination shock in December 2004 at a distance of approximately 94 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun, roughly 150 million kilometers. At 94 astronomical units, Voyager 1 was 94 times farther from the Sun than Earth is, and it was only entering the transition zone. The heliosheath itself extended for another 27 or so astronomical units beyond the termination shock, a region that took Voyager 1 roughly 8 more years to traverse. On August 25, 2012, Voyager 1 crossed the heliopause. The confirmation came not from a single dramatic instrument reading, but from a pattern of changes across multiple systems. The density of plasma around the spacecraft increased sharply, consistent with the denser interstellar medium. The intensity of low-energy particles from the Sun dropped abruptly. The direction of the local magnetic field shifted. Taken together, these measurements told scientists at JPL that Voyager 1 had done something no human-made object had ever done before. It had left the bubble of the Sun's influence and entered the space between the stars. The announcement was made in September 2013, more than a year after the crossing itself, because the data required careful analysis before the team was confident in their conclusion. There had been earlier moments when some instruments suggested the boundary had been crossed, only for subsequent readings to complicate the picture. The heliosphere does not behave uniformly in all directions. It is compressed on the side, facing the direction of the Sun's travel through the galaxy, and extended on the trailing side, giving it a shape somewhat like a comet with a long tail. Determining precisely where the boundary lay required patience and a willingness to sit with uncertainty until the evidence was clear. What Voyager 1 found on the other side of the heliopause was quieter than scientists had expected in some ways, and more surprising in others. The magnetic field in interstellar space near the heliopause was stronger than predicted. The plasma was denser. The direction of the field was not entirely what theoretical models had suggested. These were not failures of the mission. They were discoveries, the kind that only become possible when you actually go somewhere rather than simply calculating what you expect to find there. Every model of the heliosphere built before Voyager 1's crossing had to be revised afterward, not because the models were poorly made, but because the universe does not consult our models before deciding how to behave. Since crossing the heliopause, Voyager 1 has continued moving outward through what scientists call the very local interstellar medium, the region of interstellar space immediately surrounding our solar system. It is sampling a part of the galaxy that no instrument has ever directly measured. The particles it detects, the magnetic fields it measures, the plasma densities it records, all of this is data from a place we had previously only been able to infer. And the spacecraft gathering that data is running on aging systems, transmitting with a signal weaker than a refrigerator light, across a distance that grows by about 1.5 million kilometers every day. The edge of the solar system, it turns out, is not a wall or a cliff or a sudden silence. It is a gradual yielding, a long and complicated farewell, a boundary that took Voyager 1 35 years to reach, and that it crossed so quietly that it took scientists more than a year to be certain it had happened. That kind of subtlety feels appropriate, somehow, for a boundary that separates everything we have ever known from everything we have not yet begun to explore. Chapter 4. How far is far? There is a number associated with Voyager 1 that appears in nearly every article written about the spacecraft, and it is a number that resists comprehension. As of 2024, Voyager 1 is more than 23 billion kilometers from Earth. That figure is accurate. It is also, in a practical sense, meaningless to most people who encounter it. 23 billion kilometers is not a distance the human mind was shaped to understand. We evolved to navigate landscapes measured in meters and kilometers, to judge distances we could walk or ride or sail. Billions of kilometers exist outside the range of anything our intuition was built to handle, so it helps to approach the distance from a different direction. Light travels at approximately 299,792 kilometers per second. It is the fastest thing in the universe, and nothing we have ever built comes close to matching it. A beam of light leaving Earth reaches the Moon in about 1.3 seconds. It reaches the Sun in roughly 8 minutes. It reaches Jupiter in anywhere from 33 to 53 minutes, depending on where the two planets are in their orbits. It reaches Saturn in about 70 to 90 minutes. These are already distances that stretch ordinary intuition, and yet they are nothing compared to where Voyager 1 now sits. A signal traveling at the speed of light takes more than 22 hours to travel from Earth to Voyager 1. That means when mission controllers at JPL send an instruction to the spacecraft, they must wait more than 22 hours for it to arrive, and then another 22 hours for any response to return. The round trip for a single exchange takes nearly 2 full days. There is no possibility of real-time conversation. Every interaction with Voyager 1 requires a patience that most modern communication systems have trained us to forget. To put that light travel time in perspective, consider that the entire width of the inner solar system, from the Sun out to Mars, can be crossed by light in about 20 minutes. The distance to Voyager 1 is roughly 66 times greater than that. It is so far away that even describing it in astronomical units, the standard unit used for distances within the solar system, begins to feel inadequate. At more than 160 astronomical units from the Sun, Voyager 1 is so distant that the Sun itself, seen from that vantage point, would appear as nothing more than an exceptionally bright star, outshining all others, but no longer a disk, no longer a source of warmth, just a point of light in a field of other points of light. The spacecraft is traveling at approximately 17 kilometers per second relative to the Sun. That is roughly 61,000 kilometers per hour, a speed that would carry you from one side of Earth to the other in less than 40 minutes. By any terrestrial standard, it is extraordinarily fast. By the standards of interstellar space, it is almost imperceptibly slow. The nearest star system to our own, Alpha Centauri, lies approximately 4.37 light-years away. At Voyager 1's current speed, and heading in the wrong direction to reach it directly, the spacecraft would take roughly 73,000 years to cover a comparable distance. Interstellar space is not simply large. It is large in a way that makes our fastest spacecraft look stationary. And yet the distance to Voyager 1, vast as it is by human standards, represents only a tiny fraction of the distance to the nearest star. If you were to draw a map of our galaxy on a sheet of paper, with the Milky Way spanning the full width of the page, the entire distance Voyager 1 has traveled would be too small to represent with a single pen stroke. The spacecraft has left the solar system, yes, but it has barely left the neighborhood. Interstellar space begins at the heliopause, but the gravitational influence of the Sun extends much farther, out through the distant Oort cloud, a vast reservoir of comets that may reach halfway to the nearest star. In that sense, Voyager 1 has years and centuries of travel ahead before it exits the Sun's gravitational sphere of influence entirely. Distance at this scale also changes the nature of time in subtle ways. When we say that Voyager 1 launched in 1977, we are measuring elapsed time from a human perspective. But consider that the light currently reaching Earth from Voyager 1 left the spacecraft more than 22 hours ago. When we look at the spacecraft's current position on a tracking display, we are seeing where it was nearly a day in the past. Mission controllers must account for this constantly. Every calculation about where the spacecraft is, where it will be, and how to aim a signal at it must factor in the time it takes for information to travel between here and there. The spacecraft exists, in a very real operational sense, in its own temporal pocket, slightly ahead of everything we know about it. There is something quietly profound about this. Every measurement we have ever taken of Voyager 1, every data point, every photograph, every engineering reading, arrived here after a delay. We have never seen the spacecraft as it is right now. We have only ever seen it as it was. And as it travels farther, that gap between the present and our knowledge of it grows wider. It is a small preview of the fundamental challenge that will define any future attempt to explore the stars. Distance does not merely separate places. At sufficient scale, it begins to separate moments in time as well. What makes Voyager 1's distance meaningful beyond the numbers is what it represents about the reach of human curiosity. We built something, aimed it outward, and watched it go. We kept watching, kept listening, kept calculating, and 47 years later, we are still doing all three. The distance is not an obstacle that we have overcome. It is the point. The whole endeavor was always about reaching as far as possible and seeing what could be learned from out there. The answer, it turns out, is quite a lot. Chapter 5. The Deep Space Network. If Voyager 1 is one half of a conversation, the Deep Space Network is the other. It is the infrastructure that makes everything possible. The system of antennas, receivers, transmitters, and processing facilities that allows NASA and other space agencies to maintain contact with spacecraft operating far beyond Earth orbit. Without it, Voyager 1 would be silent. The data it carries would have nowhere to go. The instructions sent from JPL would never arrive. The Deep Space Network is not a supporting player in the story of Voyager 1. It is an equal protagonist. The network was established in 1963, growing out of earlier efforts to track the first generation of American spacecraft. From the beginning, its designers understood that communicating with deep space missions would require something fundamentally different from the radio systems used for Earth-orbiting satellites. The distances involved meant that signals would arrive extraordinarily weak, requiring antennas of unusual size and sensitivity. The need for continuous coverage meant that a single ground station would not suffice, and the global distribution of missions meant that the network would need to be able to reach spacecraft in any direction from Earth, at any time of day or night. The solution was to build 3 complexes, spaced roughly 120 degrees apart in longitude around the globe, so that as Earth rotates, at least one complex always has a clear line of sight to any point in the sky. The 3 sites chosen were Goldstone in the Mojave Desert of California, near Madrid in Spain, and near Canberra in Australia. Each site was placed in a relatively radio-quiet location, away from cities and industrial activity, to minimize interference with the faint signals arriving from deep space. Each complex contains multiple antennas of varying sizes, the largest of which are 70 meters in diameter, roughly the height of a 20-story building, and capable of detecting signals of extraordinary faintness. The 70-meter antennas, designated DSS-14 at Goldstone, DSS-63 near Madrid, and DSS-43 near Canberra, are among the most sensitive radio receivers ever built. Their surface area is large enough to collect even the most attenuated signals from spacecraft at the edge of the solar system and beyond. The dishes are not fixed structures. They rotate on massive azimuth bearings and tilt on elevation drives, allowing them to track a moving spacecraft across the sky with extraordinary precision. Pointing a 70-meter antenna accurately enough to maintain contact with a spacecraft more than 20 billion kilometers away requires accounting for factors that would seem negligible at shorter distances, including the slight flexing of the dish surface under wind load, the thermal expansion of the structure during the day, and the gradual drift of Earth's rotational axis over time. Operating these facilities is not a simple matter of pointing an antenna and pressing a button. Each contact session with a deep space spacecraft, called a pass, requires careful scheduling and preparation. Because the deep space network serves dozens of active missions simultaneously, ranging from Mars rovers and orbiters to spacecraft studying the Sun, Jupiter, and the outer solar system, antenna time is a genuinely scarce resource. Missions must request time in advance, and allocations are made based on mission priorities, spacecraft health, and the scientific value of the data expected during a given pass. Voyager 1, despite its age and its status as the most distant human-made object ever built, must compete for antenna time like any other mission. During a Voyager pass, the antenna is pointed to the spacecraft's predicted position in the sky, a position calculated from decades of precise tracking data. The receiving equipment is tuned to the specific frequency Voyager 1 uses to transmit, a frequency in the X-band range of the radio spectrum, around 8.4 GHz for the downlink from spacecraft to Earth. Amplifiers cooled to temperatures near absolute zero are used to reduce thermal noise in the receiving electronics, making it possible to detect a signal that arrives with a power of roughly 20 femtowatts, which is 20 quadrillionths of a watt. To put that in perspective, the energy arriving from Voyager 1 in an entire year would not be sufficient to light a single LED for a fraction of a second. Receiving the signal is only part of what the deep space network does. It also transmits commands to the spacecraft, monitors the health of the uplink and downlink, measures the Doppler shift of the received signal to determine the spacecraft's velocity, and tracks the precise timing of signal arrivals to calculate distance. The ranging data gathered during these passes is what allows mission controllers to know, with extraordinary precision, exactly where Voyager 1 is at any given moment. The position estimates are so accurate that the uncertainty in Voyager 1's location amounts to only a few kilometers, despite the spacecraft being more than 20 billion kilometers away. In recent years, the Deep Space Network has undergone significant upgrades to ensure it can continue supporting missions well into the future. New antennas have been added, existing dishes have been refurbished, signal processing systems have been modernized. The DSS-43 antenna near Canberra, the only dish in the southern hemisphere large enough to communicate with Voyager 2 due to that spacecraft's trajectory below the ecliptic plane, underwent a major refurbishment between 2020 and 2021 that temporarily suspended contact with Voyager 2 for several months while work was completed. The refurbishment was necessary to ensure the antenna could continue operating reliably for decades to come, and it illustrated something important about the relationship between the Voyager mission and the infrastructure that supports it. Keeping the conversation going requires not just maintaining the spacecraft, but maintaining the ears on the ground that are still listening. The Deep Space Network is, in its own quiet way, one of the most remarkable engineering achievements in the history of space exploration. It has been operating continuously for more than 60 years. It has supported missions to every planet in the solar system. It tracked the Apollo astronauts on their way to the Moon and received the first images from the surface of Mars. And every day, it turns its largest dishes toward a point in the sky where a small spacecraft launched nearly 50 years ago is still, improbably, transmitting. Chapter 6. Sending a Signal Across the Void. The act of sending a radio signal to Voyager 1 is, at its most basic level, a straightforward application of physics. Radio waves are a form of electromagnetic radiation, traveling at the speed of light, and they propagate outward from their source in all directions unless deliberately focused. The challenge of communicating with a spacecraft more than 20 billion kilometers away is not that the physics is exotic or poorly understood. The challenge is that the physics is unforgiving. Every factor that reduces signal strength, every source of noise, every imprecision in pointing or timing compounds across distances that leave almost no margin for error. A radio signal leaving Earth does not remain concentrated indefinitely. Even a tightly focused beam spreads outward as it travels, a phenomenon described by what engineers call the inverse square law. As a signal travels twice as far, its energy is spread over 4 times the area. At 3 times the distance, 9 times the area. The relationship is exact and merciless. By the time a signal from Earth reaches Voyager 1, it has spread across an enormous volume of space, and the tiny dish antenna on the spacecraft intercepts only a vanishingly small fraction of the total energy transmitted. The transmitters used by the Deep Space Network to reach Voyager 1 operate at powers of up to 20 kilowatts on the uplink, roughly equivalent to a powerful radio broadcast transmitter. And yet, by the time that signal reaches the spacecraft, the power intercepted by Voyager's antenna is measured in units so small they have no everyday equivalent. The frequency chosen for communication matters enormously. Radio waves at different frequencies behave differently as they travel through space and through the various layers of Earth's atmosphere. The Deep Space Network uses frequencies in the S-band, X-band, and K-band portions of the radio spectrum for different missions and different purposes. Voyager 1 communicates primarily in the X-band, at a frequency of around 8.4 gigahertz on the downlink from spacecraft to Earth, and receives commands from Earth at a lower frequency in the X-band uplink. These frequencies were chosen because they pass through Earth's ionosphere and atmosphere with relatively little absorption or distortion, and because they allow reasonably high data rates given the antenna sizes and transmitter powers available. On the spacecraft end, the transmitter that Voyager 1 uses to send its signal home is remarkably modest by any modern standard. It operates at a power of approximately 23 watts, roughly comparable to a dim incandescent light bulb. That 23 watts of radio frequency power is fed into the high-gain antenna, which focuses into a narrow beam directed toward Earth. The focusing provided by the dish antenna is what makes communication possible at all. Rather than radiating equally in all directions, the antenna concentrates the signal into a cone narrow enough to reach Earth across billions of kilometers, though even within that cone, the signal spreads considerably over such distances. Keeping the high-gain antenna pointed at Earth is one of the most critical and ongoing tasks in operating Voyager 1. The spacecraft uses a system of attitude control thrusters, small rocket nozzles that fire in brief pulses to adjust orientation, to maintain the correct pointing. Over the decades, the thrusters have fired hundreds of thousands of times to make these small corrections. By 2017, concerns had arisen about the condition of the primary attitude control thrusters, which had not been fired in continuous burn mode since 1980 during the Saturn encounter. Engineers made the decision to switch to a set of backup thrusters, known as the trajectory correction maneuver thrusters, which had been dormant for 37 years. After careful analysis, the backup thrusters were tested and found to be fully functional, a result that genuinely surprised the engineering team. The switch extended the spacecraft's ability to maintain antenna pointing and brought additional years of communication capability. The data that travels along this fragile link between Earth and Voyager 1 is encoded digitally as a stream of ones and zeros modulated onto the radio carrier wave. Error-correcting codes are applied to the data before transmission, allowing the receiving systems on Earth to detect and correct errors introduced by noise during the long journey. Without error correction, the noise inherent in any radio system operating at such extreme distances would corrupt the data beyond usefulness. With it, the stream of scientific measurements and engineering telemetry that Voyager 1 sends home can be reconstructed with high reliability, even from a signal too faint to measure with any instrument available to ordinary consumers. The data rate that Voyager 1 can achieve across this link is, by modern standards, extraordinarily slow. In the early years of the mission, when the spacecraft was closer and its power systems were stronger, data rates of up to 115 kilobits per second were possible during planetary encounters. Today, with the spacecraft farther away and its RTGs producing less power than they did at launch, the usable data rate has fallen to around 160 bits per second. That is roughly 1/10,000th the speed of a dial-up internet connection from the 1990s. At that rate, transmitting a single uncompressed photograph of the kind routinely taken by modern smartphones would take several days. The scientific data Voyager 1 returns is accordingly modest in volume. A careful trickle of plasma measurements, magnetic field readings, and engineering telemetry, selected and prioritized by the mission team to extract the maximum scientific value from every available bit. What is remarkable is not the slowness of the data rate, which is a straightforward consequence of physics and engineering constraints, but the fact that there is a data rate at all. A 23-watt transmitter on a spacecraft nearly 50 years old, operating at a distance of more than 20 billion kilometers, is still producing a signal coherent enough to carry meaningful scientific information. The physics that makes this possible is the same physics that governs every radio transmission ever made. But the precision with which that physics has been applied and the care with which every element of the system has been maintained across decades is something that goes beyond the merely technical. It is, in its quiet way, a form of devotion. Chapter 7. The 22-hour delay. There is a particular kind of patience required to work with Voyager, one that has no real parallel in ordinary human experience. When you send a message to someone on the other side of the world, the delay is measured in milliseconds. When NASA sent commands to the Mars rovers, the delay was anywhere from 3 to 22 minutes, depending on orbital geometry. With Voyager 1, the one-way travel time for a signal is currently more than 22 hours. A question asked today will not receive an answer until sometime tomorrow. And that delay grows longer with every passing day as the spacecraft moves farther from Earth. This creates an operational reality that shapes everything about how the mission is run. There is no possibility of reflexive response. If something goes wrong with Voyager 1, the team on Earth will not know about it for more than 22 hours. Once they know, any corrective command they send will take another 22 hours to arrive. The minimum time between identifying a problem and completing a response is nearly 2 full days, assuming the first command sent is exactly the right one. In practice, diagnosing an anomaly and determining the correct response often takes longer than that, meaning the actual elapsed time between a problem occurring and a solution being applied can stretch to several days or more. The team that manages Voyager 1 has developed a culture and a set of practices shaped entirely around this reality. Commands are not sent casually. Every instruction uploaded to the spacecraft is reviewed carefully, checked against simulations, and verified by multiple engineers before transmission. The consequences of sending an incorrect command are serious. A poorly formed instruction could cause the spacecraft to enter a protective fault mode, shutting down non-essential systems and reorienting itself to a default safe configuration. Recovering from such a mode requires additional commands, additional waiting, and potentially the loss of scientific data that cannot be recovered. In 2023, the mission team experienced one of the most significant anomalies in the spacecraft's recent history. Voyager 1 began returning garbled data, sending a repeating pattern of ones and zeros that carried no scientific or engineering information. The signal itself was intact. The spacecraft was clearly still functioning and still transmitting, but the data it was sending was unreadable. The team spent several months carefully analyzing the problem, sending diagnostic commands, and waiting the requisite 44+ hours for each round-trip exchange. Eventually, they traced the issue to a single corrupted chip in one of the flight data system computers, a chip responsible for storing and executing a portion of the software that formatted the outgoing data stream. The chip had not failed entirely. It had simply developed a region that could no longer reliably store the code it was supposed to hold. The solution required rewriting the affected software and relocating it to other parts of the computer's memory, a process that had to be done in carefully sequenced steps, each one transmitted separately and verified before the next was sent. The engineers who performed this work were, in many cases, not the people who originally built the system. They were working from documentation, from institutional memory, and from a deep familiarity with a computer architecture that had been obsolete for decades. The repair took months. It succeeded. In April 2024, Voyager 1 resumed returning usable engineering data, and shortly afterward, usable science data as well. It was, by any measure, a remarkable piece of remote software engineering conducted across a distance that dwarfs anything previously attempted. The 22-hour delay also changes the emotional texture of working on the mission in ways that are harder to quantify. Engineers and scientists who have spent careers listening to Voyager describe a relationship with the spacecraft that is shaped by this temporal gap. You send something out and then you wait. The waiting is not passive. It is filled with calculation, with preparation for multiple possible outcomes, with the quiet tension of not knowing. And then the signal arrives, and for a moment the gap closes, and you know something you did not know before. That rhythm of reaching out and waiting and receiving, repeated over decades, creates a kind of intimacy with the spacecraft that faster communication might paradoxically have made harder to develop. There is also something philosophically interesting about the delay that extends beyond the operational. When Voyager 1 transmits a measurement of the interstellar magnetic field, that measurement was taken more than 22 hours before it arrives on Earth. The data is always, in a precise sense, from the past. We are always learning about where Voyager 1 was, not where it is. The spacecraft exists, slightly ahead of our knowledge of it, perpetually outrunning the information it sends back. As it travels farther, this gap will grow. Eventually, when the spacecraft can no longer transmit, the last data received will represent our final snapshot of a place the spacecraft will continue to occupy, silently, long after we have stopped hearing from it. For now, though, the conversation continues. Commands go out. Data comes back. The delay is factored into every calculation, every plan, every expectation. It is simply the condition under which this particular exchange takes place, a condition unlike any other in the history of human communication, and one that the small team, still dedicated to Voyager, one has learned to inhabit as naturally as the rest of us inhabit a world where messages arrive in seconds. Chapter 8. Running on Fumes. Every machine needs energy. A spacecraft operating in the outer solar system, beyond any hope of repair or resupply, needs energy that will last not for years but for decades. When Voyager 1 was being designed in the early 1970s, the engineers responsible for its power system faced a constraint that admitted only one practical solution. Solar panels, the default choice for spacecraft operating in the inner solar system, were simply not viable at the distances Voyager 1 would travel. The mathematics were straightforward and unforgiving. Sunlight follows the same inverse square law as radio signals. At the distance of Jupiter, a solar panel would need to be roughly 25 times larger than an equivalent panel at Earth to generate the same amount of power. At Saturn, 50 times larger. Beyond Saturn, the numbers became absurd. A solar-powered spacecraft capable of operating at Voyager, one's current distance would require panels the size of a city block. The alternative was nuclear power, specifically the radioisotope thermoelectric generator, a device that converts the heat produced by radioactive decay directly into electricity. The RTG is not a nuclear reactor. There is no controlled chain reaction, no moderator, no coolant loop. It is, at its core, a remarkably simple device. A quantity of radioactive material, in Voyager's case, plutonium-238, is enclosed in a protective housing. As the plutonium decays, it releases heat. That heat flows through an array of thermoelectric elements, materials that generate a voltage when one side is hotter than the other. The resulting electrical current powers the spacecraft. The only moving parts are electrons. Plutonium-238 was chosen for specific reasons. It decays primarily by emitting alpha particles, which are relatively easy to shield against and do not produce significant gamma radiation that would interfere with the spacecraft's scientific instruments. Its half-life of approximately 87.7 years means that it decays slowly enough to provide power over the multi-decade timescales required by deep space missions, but quickly enough to generate useful amounts of heat from a manageable quantity of material. It is not a substance that occurs in meaningful quantities in nature. It is produced in nuclear reactors, and the supply available for space missions has historically been limited, a constraint that has shaped the planning of deep space exploration in ways that are not always visible to the public. Voyager 1 launched with 3 RTGs, each containing 24 pressed oxide fuel pellets of plutonium-238, for a total of 4.5 kilograms of fuel across the entire power system. At launch in 1977, the 3 RTGs together produced approximately 470 watts of electrical power. That figure has declined steadily over the decades as the plutonium fuel gradually decays. The decay is predictable, following the known half-life of the isotope, and mission planners have always been able to calculate with confidence how much power would be available at any given point in the mission. By the early 2020s, the RTGs were producing roughly 40% less power than at launch, somewhere in the neighborhood of 260 to 270 watts. Managing that declining power budget has been one of the defining challenges of the extended mission. As power availability has decreased, the mission team has been forced to make difficult decisions about which systems to keep running and which to shut down. Heaters that once kept scientific instruments and electronic components within their operating temperature ranges have been turned off, allowing some parts of the spacecraft to cool to levels that were originally considered unacceptable. Some instruments have been powered down permanently. The decisions about what to sacrifice and what to preserve have been made carefully, with an eye toward maintaining the systems most critical to both spacecraft health and scientific return. The attitude control, thrusters, which consume power every time they fire to maintain antenna pointing, have been a particular focus of power conservation efforts. Reducing the frequency of thruster firings saves power, but requires accepting slightly larger pointing errors between corrections. The engineering team has worked out the precise tolerances within which the antenna can drift before a correction becomes necessary, and they have tuned the control system to operate as close to those limits as safely possible, squeezing every additional hour of operation from a power budget that shrinks a little more each year. Despite these constraints, the spacecraft continues to operate. The RTGs are expected to fall below the minimum power threshold needed to operate any scientific instruments sometime in the late 2020s, though the exact date depends on how the power is managed between now and then. At that point, Voyager 1 will go silent, not because anything has broken, but simply because the fuel that has powered it for half a century will have decayed too far to sustain the systems needed to communicate with Earth. It will continue traveling outward through interstellar space, carrying its instruments and its golden record for billions of years after the last signal has been received. The journey will continue long after the conversation ends. There is something worth sitting with in that image. A machine built by human hands, powered by the slow decay of atoms, moving through the darkness between the stars. The power that drives it is the same process that has been occurring in radioactive materials since before Earth existed. The plutonium in Voyager's RTGs was created in the heart of a star that died long before our sun was born. It was forged in supernova and scattered across the galaxy, gathered eventually into the cloud of gas and dust that became our solar system, mined and processed and shaped into fuel pellets by people working in the 1970s and placed aboard a spacecraft that is now carrying it into interstellar space. The energy Voyager 1 runs on is, in a very real sense, older than the Sun. Chapter 9. What the data sounds like. When Voyager 1 transmits its data to Earth, it is not sending pictures. It has not taken a photograph since 1990, when it turned its cameras back toward the inner solar system one last time to capture the image that Carl Sagan would later describe as a pale blue dot. After that final portrait session, the imaging systems were powered down permanently to conserve energy. What Voyager 1 sends home today is something quieter and in some ways more profound than images. It sends measurements, numbers, a continuous, careful record of the environment through which it is passing, translated into a stream of digital data and carried across more than 20 billion kilometers on a radio wave thinner than a whisper. The instruments still operating on Voyager 1 are measuring things that no other spacecraft has ever had the opportunity to measure. The Plasma Wave Science instrument listens for oscillations in the plasma of the interstellar medium, detecting the faint vibrations that propagate through the charged particles surrounding the spacecraft. In 2012, shortly after Voyager 1 crossed the heliopause, this instrument detected a sudden increase in the density of the plasma around the spacecraft, consistent with the denser interstellar medium beyond the solar wind's reach. The detection was not visual or tactile. It was a change in the frequency of oscillations recorded by sensors that translate electromagnetic variations into data that scientists can analyze and interpret. The magnetometer measures the strength and direction of the local magnetic field. In interstellar space, this field is not generated by the Sun. It is the residual magnetic field of the galaxy itself, shaped over billions of years by the births and deaths of stars, by the movement of charged particles across vast distances, by processes operating on scales that dwarf anything in our immediate cosmic neighborhood. Voyager 1's magnetometer is sampling this field directly, providing measurements that no theoretical model could fully substitute for. The data it returns has already revealed that the interstellar magnetic field near the heliopause is stronger and differently oriented than most pre-crossing models had predicted, a finding that has prompted significant revisions in our understanding of how the heliosphere interacts with its surroundings. The low-energy charged particle instrument and the cosmic ray subsystem track the energetic particles streaming through the interstellar medium. Some of these particles are cosmic rays, high-energy particles accelerated to enormous velocities by supernova shock waves and other violent processes elsewhere in the galaxy. Others are lower-energy particles associated with the local interstellar environment. By measuring the flux and energy spectrum of these particles at Voyager 1's location, scientists can build a more detailed picture of the particle environment in the very local interstellar medium, a region that influences the structure of the heliosphere, and that plays a role in the long-term habitability of planetary systems like our own. All of this data arrives on Earth as a stream of bits, ones and zeros modulated onto a radio carrier wave, received by the large dish antennas of the deep space network, amplified, cleaned of noise, decoded, and passed to the scientists and engineers who interpret it. The raw data itself is not dramatic in appearance. It is numbers in a file, a long sequence of measurements, each tagged with a timestamp and a spacecraft identifier. The meaning of those numbers emerges only through analysis, through comparison with models and with previous measurements, through the patient work of scientists who have spent careers learning to read what Voyager is telling them. But there is one form in which Voyager's data has been made audible in a more literal sense. The plasma wave science instrument detects oscillations in the frequency range that, when converted directly to sound waves, falls within the range of human hearing. Scientists have done exactly this conversion, translating the electrical oscillations detected by the instrument into audio files that can be played through ordinary speakers. The result is an eerie, otherworldly sound, a rising and falling hiss and hum that represents the actual vibration of plasma in interstellar space. It does not sound like silence. It does not sound like emptiness. It sounds like something vast and ancient and indifferent, a medium that has been oscillating in the dark long before Earth existed and will continue long after it is gone. These audio representations are not scientific data in the strict sense. They are translations, one step removed from the raw measurements, shaped by the process of conversion into a form human ears can perceive. But they serve a purpose that pure numbers cannot. They make the data felt as well as understood. They close a small part of the enormous experiential gap between sitting in a room on Earth and floating in the interstellar medium 20 billion kilometers away. They are a reminder that the universe is not merely something to be calculated. It is something that, with enough ingenuity and patience, can be heard. The total volume of scientific data returned by Voyager 1 over its nearly 50 years of operation is, by modern standards, modest. The spacecraft's slow data rate and the long periods between antenna contacts mean that the cumulative dataset, while scientifically invaluable, would fit comfortably on a modern consumer hard drive with room to spare. What makes it precious is not its size, but its provenance. It is the only direct measurement ever taken of the interstellar medium immediately beyond our solar system. Every number in that dataset represents something we did not know before, something that could not have been calculated or inferred with confidence from any measurement taken closer to home. It is irreplaceable in the most literal sense. No other spacecraft is currently on a trajectory to reach the same region, and the next probe to cross the heliopause, whenever it is launched, will take decades to arrive. Until then, what Voyager 1 has sent home is all we have. Chapter 10. The Engineers Who Listen. Behind every data point that Voyager 1 has ever returned, behind every command successfully executed, and every anomaly carefully resolved, there are people. Not abstractions or institutions, but individual human beings who have devoted significant portions of their working lives to maintaining contact with the spacecraft, launched before many of them were born. The Voyager mission is, among other things, a story about what it means to care for something over a very long time, to inherit a responsibility from the people who came before you and to pass it on, eventually, to the people who will come after. The original Voyager team was assembled in the early 1970s, drawn from the pool of engineers and scientists who had worked on earlier planetary missions, including Mariner and Pioneer. They were, for the most part, young. The average age of the engineers working the planetary encounters in the late 1970s and early 1980s was somewhere in the mid-30s. They worked long hours during the Jupiter and Saturn flybys, processing data and solving problems in real time, operating with the kind of focused intensity that comes from knowing that the opportunity will not repeat. When Voyager 1 made its closest approach to Saturn in November 1980 and then curved away onto its outward trajectory, the team knew they were watching the end of the primary mission. What followed would be something different, quieter, longer, and in some ways more demanding. The transition from an active planetary encounter mission to a cruise mission and then to an interstellar mission required a different kind of commitment. The dramatic moments became rarer. The day-to-day work shifted toward monitoring, maintenance, and the patient accumulation of data from instruments measuring an environment that changed slowly and subtly. The team that sustained the mission through the 1990s and 2000s was smaller than the original group, and it included both veterans of the early mission and newer engineers who had joined specifically to work on Voyager in its later phase. Knowledge transfer between these generations became one of the central challenges of the extended mission. Some of the original engineers remained involved for decades. Suzanne Dodd, who became the Voyager project manager in 2010, has described the challenge of maintaining institutional knowledge about systems designed in the 1970s, using documentation that predates modern engineering software and practices. The computers on the ground that were originally used to interact with Voyager's onboard systems have long since been replaced, but the spacecraft itself has not changed. Understanding how to communicate with it requires familiarity with programming languages and computer architectures that are no longer taught, with hardware interfaces that were obsolete before the internet existed. and with a body of accumulated operational knowledge that exists partly in documents and partly in the memories of people who have been working with the spacecraft for 30 or 40 years. This creates a genuine preservation challenge. As the engineers who built and first operated Voyager, one have retired or passed away, the knowledge they carried has had to be carefully extracted, documented, and transmitted to successors. Some of that knowledge transfer has gone smoothly. Some has been imperfect. There are aspects of Voyager 1's behavior, particular quirks in how it responds to certain commands or certain conditions, that are understood today primarily because someone who remembered the original design decisions was still available to explain them. As that generation recedes, the mission team relies increasingly on documentation and on the accumulated record of decades of operational experience. The 2023 anomaly that produced garbled data from Voyager 1 illustrated both the challenge and the capability of the current team. The engineers who diagnosed and resolved the problem were working with a computer system that had not been modified in any fundamental way since the 1970s. They were writing code in a language and for an architecture that no university currently teaches. They were doing so under the constraint of a 44-hour round-trip communication delay, which meant that every diagnostic step had to be carefully planned in advance, with contingencies prepared for multiple possible outcomes. The fact that they succeeded, that they identified a corrupted memory chip from 20 billion kilometers away and rewrote the affected software to work around it, speaks to a depth of expertise that is difficult to overstate. There is also an emotional dimension to this work that the engineers themselves have spoken about with some candor. Voyager 1 is not merely a machine to the people who work with it. It is something they have tended for years or decades, something they have worried about and celebrated and grieved over in small ways. When the spacecraft went silent with garbled data in 2023, the distress felt by the team was real. When the signal came back clean in 2024, the relief was equally real. These are not sentimental projections onto an indifferent object. They are the natural consequence of sustained attention and care over long periods of time. You cannot spend years listening to something without developing a relationship with it. The team that works on Voyager 1 today is small, a handful of engineers and scientists who divide their time between Voyager and other missions. They are aware that they are likely among the last people who will ever communicate with this spacecraft. The window remaining is measured in years, not decades. When the RTGs finally fall below the threshold needed to sustain communication, whoever is on shift that day will receive the last signal from Voyager 1, process it, and file it. And then the antenna will move on to the next scheduled contact with some other spacecraft in some other part of the solar system. And Voyager 1 will continue its journey in silence, carrying with it the accumulated attention of everyone who ever listened. Chapter 11: Voyager 2 and the Parallel Journey. When people think about the Voyager program, they most often think about Voyager 1. It is the father of the two spacecraft, the holder of the record for the most distant human-made object, the first to cross the heliopause. It receives the majority of the attention and carries most of the symbolic weight of the mission in popular imagination. But Voyager 2 has its own story, and in several important respects, it is the more scientifically remarkable of the two probes. Understanding the Voyager mission fully requires spending some time with the spacecraft that launched first, traveled more slowly, and quietly accumulated a scientific legacy that its more famous twin cannot match. Voyager 2 departed Earth on August 20th, 1977, 16 days before Voyager 1. Its trajectory was designed differently from the start. where Voyager 1 was aimed for a fast path to Jupiter and Saturn, with a close flyby of Saturn's moon Titan that would bend its trajectory out of the ecliptic plane and onto its current outward path. Voyager 2 was placed on a slower trajectory that preserved the option of continuing to Uranus and Neptune. This flexibility came at the cost of speed. Voyager 2 would take longer to reach Jupiter and Saturn, and it would never travel as fast as its twin. But if the spacecraft remained healthy after Saturn, it would have the opportunity to do something no spacecraft had ever done: visit all 4 of the solar system's outer planets on a single mission. The spacecraft remained healthy. Voyager 2 flew past Jupiter in July 1979, returning images and data that complemented and extended what Voyager 1 had gathered 4 months earlier. It passed Saturn in August 1981, conducting its own survey of the planet's rings and moons before continuing outward. In January 1986, it became the first spacecraft to fly past Uranus, returning the only close-up images of that planet and its moons ever taken. In August 1989, it completed the Grand Tour with a flyby of Neptune, passing within 5,000 kilometers of the planet's north pole and conducting a close observation of the large moon Triton. Those Neptune and Uranus encounters remain, to this day, the only close observations ever made of those 2 planets. No follow-up mission has yet reached either of them. The data returned during those encounters reshaped our understanding of the outer solar system in ways that are still being processed decades later. At Uranus, Voyager 2 discovered 10 previously unknown moons and 2 new rings. It revealed that the planet's magnetic field is dramatically tilted relative to its rotational axis, offset by nearly 60 degrees, a configuration unlike anything seen at any other planet and still not fully explained. At Neptune, the spacecraft discovered 6 new moons, confirmed the existence of a ring system, and observed a large storm system in the planet's atmosphere that scientists named the Great Dark Spot. It also revealed that Triton, Neptune's largest moon, has a tenuous nitrogen atmosphere and active geysers that eject material several kilometers above the surface, making it one of the most geologically active bodies in the outer solar system. After Neptune, Voyager 2 followed its own outward trajectory, heading in a different direction from Voyager 1 and sampling a different region of the heliosphere as it traveled. This turned out to be scientifically valuable in ways that had not been fully anticipated. The heliosphere is not symmetric. It is shaped by the sun's movement through the galaxy and by the varying pressure of the interstellar medium in different directions. By having 2 spacecraft crossing the heliopause at different locations, scientists gained the ability to compare conditions on opposite sides of the boundary, building a more complete picture of the heliosphere's overall structure than either spacecraft could have provided alone. Voyager 2 crossed the heliopause in November 2018, about 6 years after Voyager 1. It did so at a distance of approximately 119 astronomical units from the Sun, somewhat closer than the 122 astronomical units at which Voyager 1 made its crossing. The difference in crossing distances confirmed that the heliopause is not a uniform sphere. It is compressed and asymmetric, pushed inward in some directions by the pressure of the interstellar medium and extended outward in others. The simultaneous operation of both spacecraft in interstellar space, even at their considerable separation, has allowed scientists to distinguish between local variations in the interstellar environment and broader structural features of the heliosphere itself. One of the most significant differences between the 2 spacecraft is their visibility from Earth. Because of the trajectory Voyager 1 took after its Saturn flyby, it travels above the ecliptic plane, the flat disk in which the planets orbit. Voyager 2, by contrast, travels below the ecliptic, heading into the southern celestial hemisphere. This means that Voyager 2 can only be tracked by antennas in the southern hemisphere, specifically the 70-meter dish at the Deep Space Network Complex near Canberra, Australia. When that antenna underwent its major refurbishment between 2020 and 2021, contact with Voyager 2 was suspended for several months, a period during which the spacecraft continued operating autonomously, following preloaded instructions without receiving any new commands from Earth. The two Voyager spacecraft are now traveling in roughly opposite directions, sampling different regions of interstellar space and providing what amounts to a two-point survey of the environment immediately beyond our solar system. The data they return, compared and analyzed together, is more valuable than either dataset alone. They are, in this sense, still operating as a system, still fulfilling a collaborative purpose, even as they move farther apart with every passing year. Two small machines, launched within weeks of each other nearly half a century ago, still talking to each other through the data they send home, still illuminating the same questions from different angles, still doing the work they were built to do. Chapter 12. When contact will end. There is a date somewhere in the future, not precisely known, but narrowing with each passing year, when Voyager 1 will transmit its last signal to Earth. The spacecraft will not explode or crash or dissolve. It will simply run out of the power needed to operate the systems that keep it communicating. The RTGs will have decayed too far to sustain the transmitter, the computers, and the instruments. One by one, over a period of years, the remaining systems will be shut down or will fail, and eventually the signal that has been crossing interstellar space for nearly half a century will stop. The antenna will still be there, pointed at a sun too distant to warm it. The golden record will still be attached to the spacecraft's frame, but the voice will be gone. The timeline for this ending is not a mystery. It is a calculation, grounded in the known decay rate of plutonium, 238, and the measured power consumption of Voyager 1's remaining systems. The RTGs lose roughly 4 watts of power per year as the fuel decays. That rate is predictable and has been consistent with expectations throughout the mission. The mission team tracks the available power budget continuously, comparing it against the power requirements of each operating system and making adjustments when necessary to extend the useful life of the spacecraft as long as possible. By the early 2020s, the power situation had become tight enough that the team began shutting down heaters for scientific instruments, allowing some components to operate in conditions colder than their original design specifications. This was a calculated risk, taken after careful analysis, suggested that the instruments could continue functioning despite the lower temperatures. The gamble paid off. The instruments continued to return data even as the spacecraft grew colder. But it illustrated how little margin remained and how carefully every watt had to be managed. The current projections suggest that Voyager 1 will need to shut down its remaining scientific instruments one by one over the course of the mid to late 2020s, as the power budget continues to decline. Each instrument shutdown represents a permanent loss. Once an instrument is powered down, it will never be turned on again. The data it could have gathered during the remaining years of operation will simply not exist. The mission team faces these decisions with the same careful deliberation they have brought to every operational choice over the decades. weighing the scientific value of each instrument against the power cost of running it and the benefit of preserving power for the systems needed to keep the spacecraft communicating at all. After the instruments are gone, the spacecraft may continue transmitting engineering telemetry for some additional period, sending home data about its own health and status, even after it has nothing left to measure in the interstellar medium. That telemetry, while scientifically less valuable than the instrument data, provides information about the spacecraft itself that engineers find useful, and it maintains the connection for as long as possible. Eventually, though, the power available will fall below even the minimum threshold needed to operate the transmitter, and the signal will stop. The exact date of final silence is not fixed. It depends on how aggressively the team manages the power budget, which instruments are prioritized and which are sacrificed, and whether any unexpected failures occur before the power runs out naturally. Current estimates place the end of the mission somewhere in the late 2020s, though some optimistic scenarios extend into the early 2030s. The uncertainty is real but bounded. Whatever the precise date turns out to be, the people working on the mission today are aware that they are likely working through the final years of a project that began before most of them entered the workforce. What happens to Voyager 1 after the signal ends is, in one sense, straightforward. The spacecraft will continue traveling in the same direction at the same speed, decelerating imperceptibly under the sun's gravity, but effectively maintaining its current velocity for the foreseeable future. In approximately 300 years, it will reach the inner edge of the Oort cloud, the distant reservoir of comets that marks the outermost gravitational boundary of the solar system. It will take roughly 30,000 years to pass through the Oort cloud entirely. In approximately 40,000 years, it will pass within 1.6 light-years of a dim red dwarf star called Gliese 445, which is itself moving toward our solar system and will be considerably closer by then than it is today. Beyond that, Voyager 1 will continue outward into the galaxy, carrying its instruments and its record for a period of time that makes the entire history of human civilization look like a brief footnote. The golden record, mounted on the spacecraft's frame, is expected to remain intact for at least 1 billion years in the relative emptiness of interstellar space. The primary threat to its survival is not corrosion or decay, which require an atmosphere and liquid water to proceed at meaningful rates. It is the slow erosion of micrometeorite impacts, dust-sized particles drifting through interstellar space that will gradually pit and abrade any exposed surface over geological timescales. Even so, the record's information is expected to remain largely recoverable for an enormous span of time, longer than Earth has existed, longer than the sun has left to burn. There is something quietly extraordinary about sitting with that fact. The conversation between Voyager 1 and the people who built it will end within a few years, but the object itself and the message it carries will persist long after the last person who ever worked on the mission has been gone for millions of years. We are, without quite intending to, writing something permanent. The signal ends. The journey does not. Chapter 13. What Voyager taught us about interstellar space. Before Voyager 1 crossed the heliopause in 2012, everything we knew about the interstellar medium immediately beyond our solar system was inferred. We had theoretical models, built from observations of distant stars and from measurements taken within the heliosphere itself. We had calculations about what the density, temperature, and composition of the local interstellar medium ought to be, based on what we could observe from a distance, and what we understood about the physics governing such environments. Those models were careful and sophisticated, the product of decades of work by some of the best minds in astrophysics. And they were, in several important respects, wrong. Not catastrophically wrong. The broad picture they painted was accurate enough. The interstellar medium is indeed a thin cold plasma, far less dense than anything we would recognize as matter in everyday experience. The magnetic field threading through it is indeed shaped by the large-scale dynamics of the galaxy. The cosmic rays arriving from distant sources do indeed fill interstellar space with high-energy particles. These things were known, or at least strongly suspected, before Voyager 1 arrived to confirm them. What the spacecraft revealed was the detail, the texture, the specific quantitative reality of a place that had previously existed only as an abstraction in scientific literature. The first, and perhaps most immediately significant finding, was the structure of the heliopause itself. The boundary between the solar wind and the interstellar medium turned out to be thinner and more sharply defined than many models had predicted. Rather than a broad, gradual transition zone, Voyager 1 found a relatively abrupt change in plasma density and magnetic field direction over a comparatively short distance. This sharpness suggested that the interaction between the solar wind and the interstellar medium was more dynamic and better organized than some theoretical frameworks had assumed. The models were revised accordingly, with implications for our understanding of how other stellar systems interact with their surrounding interstellar environments. The magnetic field in the local interstellar medium provided some of the most surprising data. Before Voyager 1's crossing, the expected orientation of the interstellar magnetic field near the heliopause had been estimated from observations of polarized light, from distant stars, and from other indirect measurements. The actual orientation Voyager 1 measured differed from those estimates by a meaningful amount. The field was also stronger than the most widely cited pre-crossing predictions, though it fell within the range of uncertainty acknowledged by more cautious models. These discrepancies prompted a re-examination of the methods used to infer interstellar magnetic field properties from remote observations, leading to refinements in technique that benefit not just heliospheric science, but the broader study of interstellar magnetic fields throughout the galaxy. The plasma density measurements returned by both Voyager spacecraft have been particularly valuable. The interstellar medium is not uniform. It contains regions of varying density, temperature, and composition, shaped by the history of stellar activity in the local neighborhood of the galaxy. Our solar system currently sits within a region called the local interstellar cloud, a slightly warmer and denser pocket of gas embedded within a larger structure known as the local bubble, itself the remnant of one or more supernova explosions that occurred within the past few million years. The plasma measurements from Voyager 1 and Voyager 2 are helping scientists map the properties of the local interstellar cloud with a directness that no remote observation can match. The cosmic ray environment in the very local interstellar medium has also been characterized with new precision. Inside the heliosphere, the solar wind partially shields the inner solar system from low-energy cosmic rays arriving from outside. This shielding effect, known as solar modulation, means that the cosmic ray flux measured near Earth is not representative of the flux in interstellar space. Voyager 1's instruments, operating beyond the heliopause, have measured the unmodulated cosmic ray flux directly for the first time, providing a baseline that researchers studying cosmic ray propagation through the galaxy have been eager to have for decades. The measurements have confirmed and refined theoretical predictions about the energy spectrum and composition of low-energy cosmic rays in the local interstellar medium, Perhaps the most consequential scientific legacy of the Voyager interstellar mission is not any single measurement, but the cumulative effect of having direct data from beyond the heliopause at all. Before 2012, the boundary of the solar system was a theoretical construct, a line on a diagram. After 2012, it became a place that had been visited and measured. The transition from inference to direct observation is not merely a philosophical distinction. It changes the confidence with which we can build models, the precision with which we can test predictions, and the depth of our understanding of the environment in which our solar system exists. That understanding has practical implications that extend beyond pure science. The heliosphere plays a role in protecting the inner solar system from the most damaging components of the cosmic ray flux. Understanding how the heliosphere interacts with the interstellar medium, how its size and shape respond to changes in solar activity and to variations in the local interstellar environment, is relevant to questions about the long-term habitability of Earth and similar planets around other stars. A star moving through a denser region of the interstellar medium would have a compressed heliosphere, offering less shielding to its planets. A star passing through a region like the local bubble might have an expanded heliosphere offering more. The data from Voyager feeds directly into these broader questions about the conditions under which life can persist over geological timescales. All of this knowledge flows from a spacecraft launched in 1977 with instruments designed to study the outer planets, kept alive by a team of dedicated engineers, and guided by the quiet persistence of people who believed that the data it could return from the edge of the solar system and beyond was worth the decades of effort required to receive it. The scientific return of the Voyager interstellar mission was not guaranteed when the spacecraft launched. It was earned incrementally through nearly 50 years of careful work. What we know about interstellar space today that we did not know before is a direct measure of that effort, and it will inform the design of every deep space mission that follows. Chapter 14. Still out there. There is a point in space, somewhere beyond the heliopause, where a small gold-colored spacecraft is moving through darkness so complete that the sun behind it is indistinguishable from any other star. No light reaches it with enough strength to cast a shadow. No sound travels through the near-perfect vacuum surrounding it. The temperature of the space around it is close to absolute zero. And yet, somewhere inside the aging electronics of that spacecraft, a transmitter is running, powered by the slow decay of atoms older than the Earth, and it is sending a signal home. That signal is traveling toward us right now. It left Voyager one more than 22 hours ago, moving at the speed of light across a distance that no human being has ever physically traversed, and none ever will in any foreseeable future. It will arrive at one of the large dish antennas of the Deep Space Network, be amplified and cleaned of noise, decoded and processed, and passed to a small group of people who will read it the way a doctor reads a patient's chart, looking for signs of health, for changes in the numbers, for anything that requires attention, and then tomorrow they will do it again. This is, when you step back from the technical details and the engineering vocabulary, a remarkable thing to contemplate. We built something small enough to fit in a large room, launched it into space nearly 50 years ago, watched it travel past the outer planets and through the heliosheath and across the heliopause, and we are still in contact with it. The conversation has never stopped. It has slowed, grown quieter, become more careful and deliberate as the years have passed and the distance has grown. But it has continued. What does it mean that we have done this? It is worth asking the question slowly without rushing toward an answer. One way to think about it is in terms of the scale of human attention. Civilizations rise and fall over centuries. Technologies become obsolete within decades. Individual human careers span 30 or 40 years at most. And yet, the Voyager mission has outlasted the careers of everyone who built it, adapted to technologies its designers never imagined, passed through the hands of multiple generations of engineers, and continued returning data. It is one of the longest continuously operating scientific endeavors in history, and it is still going. The attention that human beings have collectively paid to this one small spacecraft, maintained across half a century and passed from person to person like a carefully tended flame, is itself something worth noticing. Another way to think about it is in terms of what Voyager 1 represents about the nature of curiosity. The mission was not launched because anyone knew what would be found beyond the heliopause. The scientists who designed the instruments and the engineers who built the spacecraft were working in genuine uncertainty about what Voyager would encounter as it traveled outward. The decision to keep the mission going, to maintain contact through the long, quiet years between planetary encounters and on into the interstellar phase, was a decision to keep asking questions even when the answers were slow in coming. That kind of sustained curiosity, patient and unhurried and committed to the long view, is rarer and more valuable than it might appear. There is also something worth holding in the image of the golden record, still attached to the spacecraft's frame, still traveling outward through the dark. It will almost certainly never be found. The probability of Voyager 1 coming close enough to another inhabited world for its cargo to be discovered, within any time frame meaningful to human history, is so small as to be effectively zero. The people who placed the record on the spacecraft knew this. Carl Sagan and his colleagues were not naive about the odds. They included it anyway, not because they expected it to be found, but because the act of including it said something true about what human beings are. We are the kind of creature that reaches out. We are the kind of creature that, when given the opportunity to send something beyond the boundaries of the known, chooses to include music and greetings and the sound of rain and the recorded heartbeat of a person in love. We choose to say, to no one in particular, and to anyone who might someday listen, that we were here, and that we wondered, and that we cared. Voyager 1 is expected to fall silent within the next few years. The power will decline below the threshold needed to sustain communication, and one day the signal will not come. The team at JPL will know, because they will have been tracking the power budget carefully, watching the numbers approach that threshold with the quiet attention of people who have been preparing for a loss they have long understood was coming. They will receive the last data, process it, and archive it. And then the mission, in the operational sense, will be over. But the spacecraft will not stop. It will continue outward, through the local interstellar cloud and the local bubble, and into regions of the galaxy we have no name for yet, carrying its instruments and its record, and the accumulated curiosity of the people who built it and tended it and listened to it for half a century. In 40,000 years, it will pass near another star. In 1 billion years, the golden record will still be largely intact, waiting in silence for something that may never come, and that was never really the point. The point was the reaching. The point was the decision, made in the early 1970s by a group of people working at the edge of what was technically possible, to aim something at the darkness and keep listening for as long as they could. The point was every engineer who inherited that responsibility and carried it forward. The point was every data packet received, every anomaly diagnosed, every careful command sent across 20 billion kilometers, of empty space. The signal is still traveling. The spacecraft is still out there. And for a little while longer, we are still listening. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.